I am Sydney Tucker, and today I will be discussing psychopharmacology. Psychopharmacology, as defined by Carlson and Burkett in Physiology of Behavior, is the study of the effects of drugs on the nervous system and behavior. In their definition, a drug is an exogenous chemical not necessary for normal cellular functioning that significantly alters the function of certain cells of the body when taken in relatively low doses. We take a look at the process of pharmacokinetics, in which a drug is absorbed, either intravenous injection, orally, through inhalation, or even insufflation. And then, once that drug is absorbed, it gets distributed throughout the body until it reaches the site of action where the drug actually interacts with the body. And as that's occurring, enzymes come to metabolize the drug so that it can be excreted from the body. A drug is metabolized and excreted from the body. It interacts within the cells and causes certain effects. As shown by figure 4.4, a dose-response curve plots the points between the dose of the drug and the effect of the drug, and the curve comes as the dose of the drug can no longer cause a higher effect. And then this further relates to the therapeutic index of a drug. In figure 4.5, the dose-response curve for morphine is used as an example to show how the therapeutic index for a drug is computed. First curve focuses on the medicinal effects of morphine that are wanted when used, while the second curve focuses on the more toxic effects that could occur while using this specific drug. Once these two are found, then a ratio between the percentage can be made to determine how safe that drug is. The lower a therapeutic index is, the more likely a drug has in creating toxic effects for the body. Toxic effects become more of a potential problem with repeated use with the drug. As a person consumes the same drug repeatedly, the body starts to build tolerance to some of the effects. And as tolerance grows, if the individual tries to stop, there can be withdrawal symptoms as the body has started to change the way it operates to make up for the consistent amount of drug that's in the system. And once withdrawal symptoms are present, that individual now has a physical dependence on that drug because the brain has altered its state of activity in response to the continuous presence of the drug. And in some cases, while it is not as common as tolerance, some drugs can cause an effect called sensitization, where the effect of the drug actually becomes more potent with more use. Most drugs are able to cause an effect in the body by impacting the processes at the synaptic transmission. Drugs that impact the synaptic transmission are generally classified into either antagonists or agonists. The drugs that work as antagonists inhibit postsynaptic effects, while the drugs that are agonists aid the postsynaptic effects. These two categories can be broken down even further into either direct or indirect. A direct agonist or antagonist works by taking the place of a specific neurotransmitter. Those that work indirectly attach to an alternative site but create the same end effect. Drugs affect the production of neurotransmitters as seen by 1 and 2 in figure 4.7, where an agonist can work to create more of a specific neurotransmitter, or on the flip side, an antagonist can work to keep specific neurotransmitters from being created. Moving on to parts 3, 4, and 5, we can see the effect that drugs can have on storage and release of neurotransmitters. Certain drugs are able to keep vesicle transporters from filling up with neurotransmitters in the first place, which would obviously keep them from being released because the transport vesicle is empty. Then drugs can also impact the release points and either facilitate that release or keep it from occurring. Ways in which drugs affect receptors is a bit more complex, but 6, 7, 8, and 9 of figure 4.7 show the ways in which drugs can have effect on either postsynaptic receptors or presynaptic receptors, or labeled as autoreceptors on figure 4.7. The drugs can either increase the amount of neurotransmitters being released or block the amount of neurotransmitters being released. And then following back on the postsynaptic receptors, drugs can increase the amount of neurotransmitters received, or they can block the amount of neurotransmitters being received. Lastly, drugs can either affect the reuptake, as shown by 10, or the destruction of neurotransmitters, as shown by 11. After neurotransmitters are released from the cell, they have to be cleared away. Some are reuptaken by the cell and others are destroyed by enzymes. 10 shows how a drug can interfere with the reuptake process, while 11 shows how a drug can interfere with the enzyme's ability to remove the neurotransmitters. It is helpful to know the most common neurotransmitters found in the human body. Table 4.1 lists the most common. These neurotransmitters are then a part of different neurotransmitter systems. The amino acid system is comprised of glutamate and GABA. These are the two most important neurotransmitters in the central nervous system, and they work as on and off switches. Acetylcholine is part of the acetylcholine system, and this neurotransmitter is unique in that it affects the central and the peripheral nervous system. Following that are the monoamines. The neurotransmitters that make up the monoamine system are dopamine, norepinephrine and epinephrine, serotonin, and histamine. These neurotransmitters are fairly similar to one another, and so drugs that impact one of them can often impact the others as well. This neurotransmitter system is the peptide system. Within this system are opioid neurotransmitters, which, as we all know, play strongly in pain relief. And lastly, there are the lipid neurotransmitter systems. And one of the most common neurotransmitters in this system is the endocannabinoids. Another well-known transmitter for aiding in pain regulation, but also playing a major part in appetite regulation. And that wraps up our discussion on psychopharmacology. Thank you for listening.